Hey, welcome to week 4 and Mesozoic Tectonics. Woohoo, let's reunite Pangaea. Of course, Pangaea is the continent of all continents. Well, this week, the objectives are to identify the distribution of tectonic plates at the beginning of the Mesozoic. We're going to show how the margin of Western North America transitions from a passive to an active margin then in the early Mesozoic. And then we're going to look at the progressive development of structures across the western U.S. During the Mesozoic. Pretty straightforward this week. So at the end of the Paleozoic, there was one continent, Pangaea, and one ocean. So if you take a look, that's a pretty nice diagram, kind of shows the current country boundaries in all of the continents all mashed together over here, then with a more simplified version over here. And of course, here we are up in Alaska right there, right? And but a pretty neat layout. So this is the planet at the end of the Paleozoic. And of course, that's the time period we are interested in because it's the transition from the Permian, right, into the Triassic that things are starting to get interesting along this west coast of Pangaea. So zooming in on that part of the world, we see that the region we are interested in, right, is this westernmost edge of Pangaea. And this, since Pangaea more or less straddled the equator, the area we're interested in is just north of the equator, right? And because, I don't know if you've had any geography or not, but when you move away from the tropics, the center tropical belt on the planet, you get into deserts. And that has to do with the direction of the winds and the high and low pressure. But anyway, just north of the equator, in the late Permian, right, North America region was mostly an arid area, right? And any kind of shallow seas that encroached upon the continent at this point, it was pretty arid, so we're going to end up with evaporite deposits. So if you look around places like Las Vegas, right, Western North America in the late Permian, what was this arid region of, not an aid region, that's supposed to be arid. Here, look, I'll fix it for you right while I'm talking. There you go, how's that? All right. Western North America in the late Permian was an arid region with shallow seas and evaporites. This is the same time frame as that rim of the Grand Canyon. Now, when you go to the Grand Canyon, you won't see these same rocks. You'll see limestones, and these rocks in the background here, pictures are a little grainy, but these are all Kaibab limestone near Las Vegas. This is actually just west of Las Vegas. In the Grand Canyon, you'll also see the Kaibab limestone. That is the upper rim of the canyon, but you won't see gypsum there. These limestones, these Kaibab limestones, are full of thick gypsum units which were deposited in those shallow seas, right, as those shallow seas evaporated. So that's pretty cool. And what this plant is out here, this is a gypsum wallboard plant. And the gypsum is mined up here on the cliffs, and then it's brought down to the plant in this conveyor belt, and then the plant crushes it up and puts it in these big sheets and bakes it in these big ovens. Anyway, so the wallboard that you're putting in your houses is the result of evaporites forming on that western margin of Pangaea. Pretty cool. So don't forget that the time frame that we're talking about is right here at the Triassic boundary, right? The Permian and the Triassic. And of course, the Permian is the last period of the Paleozoic era. And of course, the Paleozoic comes to a close. Why? Why do we draw the boundary here between the Paleozoic and the Mesozoic? Well, that's because there was a very large extinction event, right? The Permian mass extinction, and where 99%, it's postulated, of all life perished. Sounds dramatic, and I'm sure it was. What caused it? I don't think anybody knows. I mean, it could have been like, this is the famous extinction up here at the end of the Mesozoic, right, where the dinosaurs did it along with a bunch of other stuff. And that's now debated to be whether it's volcanic eruptions or volcanic eruptions with a meteor. But anyway, this is where we are. Pangaea, end of the Permian. There's a giant mass extinction event. And of course, what happens after that mass extinction? Well, the dinosaurs take over, reptiles, right? First little ones, then transitioning to larger ones later on in the Mesozoic, but at first it would have been these, multiple species of small dinosaurs that sort of fanned out across the face of this supercontinent that had experienced this large extinction event. So they adaptively radiated out to fill up these niches. So in the early part of the Mesozoic, shallow seas and deserts covered western Pangaea, and life, of course, was diversifying across this big landmass. When we move up into the early Triassic, we see that the Pangaea is still intact, but it's starting to break up. And what I show you here is between Africa and Antarctica, you see this rift that's happening in here, as well as a continental rift that's starting to form between North America and Africa and South America. And of course, this is going to become the Atlantic Ocean, but this is important because Pangaea is intact. The climate is such, again, you can see where the equator is going here, where we've got these desert regions, but Pangaea is starting to break up. So when you get up into the early Jurassic, right, Pangaea will break up into two separate land masses. The northern continents, this is all going to be, it's a little hard to read in here, but this is Laurasia, right, and that's North America and Asia together, and Europe. And then the southern continent of Gondwana, or Gondwanaland. And that's down here, with South America, Africa, Antarctica, Australia, and India all together. So these continents, as they break up, right, as Pangaea breaks up into north and south, and then ultimately into those parts, or even into east and west, the important thing to notice is the development of these rift zones. Okay, those rift zones are really important for the southwestern U.S. because what's going to happen is as those rifts grow, they're going to take up room in the ocean. So as the continents moved apart, there was an intense period of plate tectonic activity, and seafloor spreading was so vigorous that the mid-ocean ridges basically fill up the oceans, and without any other place for that water to go, the water transgresses onto the continent. So what we're going to see in the later part of the Mesozoic are marine transgressions and regressions. So we're going to start to see more sediment on those continents again. Now, simultaneously, during most of the Mesozoic, along the western margin of Laurasia and Gondwanaland here, what we see is a subduction zone. And so the plate out here, which ultimately is going to become the Farallon plate, is moving eastward and subducting along the western margin of Laurasia and Gondwanaland. That's going to create a volcanic arc. And at first, it's an island arc. So what we're going to see is an arc of volcanoes, and that's all part of these accreting terrains that are going to attach themselves on and form Alaska and parts of California. So these North America collided with island arcs and microcontinents, and so what ends up happening is we basically are getting these mountain ranges accreting onto the continent's western edge. That's going to form the westernmost part of North America during this time frame. So the subduction of the the Farallon plate, right? The oceanic Farallon plate beneath western North America during the late Jurassic and early Cretaceous. This is going to produce igneous intrusions, volcanoes, of course, as well, and metamorphic rocks. Now, today, if you want to go see those intrusions, right, they've been uplifted and they're exposed, at least in the areas we're going to travel, down here in the Sierra Nevada mountain range. Now, those same intrusions from Mesozoic subduction and magmatism can be found all the way from the tip of Baja down at Cabo, all the way up through California, here in the Idaho batholith, and then the coast ranges leading all the way up through Canada and up into Alaska. Because remember, that whole western margin of Pangaea and then later Gondwanaland and Laurasia have an active margin on its western edge. So here's another couple of diagrams showing basically the same thing. Here is a view, there's North America, right? This is the area that we're talking about. Here's that subduction zone. Here's the Farallon plate, and it's being rifted eastward and subducting under North America. And of course, on these diagrams, this is some of those paleogeographic diagrams I showed last time. Here you can see all these different continental slivers and slices and island arcs and stuff that have accreted onto western North America. The pink is the old rocks. That would be the Precambrian rocks, right, from our talk on geologic history. All of this stuff is much younger that got slammed on there in the later part of the Paleozoic and during the Mesozoic. So you can see what the margin of western North America would have looked like, you know, sort of during the Mesozoic. So during this time frame of a subduction zone, an active margin, what we see, here's Triassic, right, the earlier part of the Mesozoic. You're going to see a whole bunch of volcanoes, island arcs, little continental slivers that are going to be pushed into the western side of North America. So sedimentary wise, right, if we think about the sediments that are going to be deposited during this kind of time frame, what we find is a western belt of volcanic rocks and greywackies. They're associated with the volcanic arcs. Now those rocks today are the Franciscan group rocks in western California along the coast ranges. Then there's an eastern belt of shallow marine sandstones and limestones, right, closer to the mainland. You're going to find this kind of stuff out through Nevada. And then finally, further east, these are going to be non-marine continental red beds are going to be deposited sort of on a low alluvial plains of the continent. And those are the rocks we're going to end up seeing around Utah. So here's a shot looking back at Zion National Park, or right about the beginning, the sort of the southern part of Zion National Park. And I've combined a photograph from my collection and the stratigraphy, the Mesozoic stratigraphy in that region. So here's Triassic and Jurassic rocks, starting with the Moenkopi, then the Shinarump, Chinle, Wingate, Kayenta, and finally the Navajo Sandstone. And here it is, the top of this peak, and this is the highest part in Zion. There's the Navajo Sandstone, there's the Kayenta formation, which is mostly sandstone, and the Wingate. This gray area down here at the bottom, that's the Chinle group. Okay, that's mostly the painted desert. That's ashes and the petrified forest. And then this sharp edge right there, that's the Shinarump conglomerate. And then this stack of red and white sort of beds here you can see in the foreground here. All of this slope, that's the Moenkopi. These were the red beds that were deposited on the continent, right, during the time frame that to the west was being, you know, in the arc, and also mountain ranges that were sort of down warping. So if we look at the Jurassic and the Cretaceous, right, we see that, again, there's shallow seas, and where are these seas coming from at times, right? The sea can come in there and deposit, material because of these active spreading ridges expanding and making the water sort of flood out onto the continent. By the time we get to the Cretaceous, we've got a pretty good mountain range going over here to the west. This is a good size orogeny. We're going to talk about the Sevier orogeny. That's it. And then on the inland side here, we're going to see downwarping basins that are receiving at sometimes marine sediment, shallow marine sediment, and other times continental sediments. So in the late Cretaceous, right, the last period of the Mesozoic, this mountain building is going to sort of reach its peak. And here I say that in Western North America, you got a range of high mountains. These are sort of rocky mountain size, big mountains, right, formed as the result of orogenies that had begun way back in the Jurassic. As the mountains eroded, thick sequences of sediment, up to 9 miles thick, that's pretty amazing, right, accumulated in rapidly subsiding basins. Why are the basins subsiding? Because the mountains are pushing up, and that's creating basins on the side. So the rocks were folded and intruded. These same sediments were then folded and intruded by granites, right, as a result of continuing tectonic deformation during the Middle and Late Cretaceous. Let's see if this diagram helps you. So imagine during the Mesozoic, this is Western North America. We got the ocean here. We got a subduction zone with a trench, right? Just like the forearc set situation we have in Anchorage today, right? We've got these faults in the accreting sort of terrains and scraping up off the trench here of these forearc sediments. We've got melting certainly going on, intrusion of batholiths. At the time, there would have been volcanoes, and that ash is drifting east and falling into these shallow seas. Further east, we see a lot of this sediment that was deposited being faulted, thrust faulted. Now, this also includes the older sediments from the Paleozoic, right? And all of this is getting buried by younger sediments that are getting faulted and folded as well until we finally reach out here further to the east. No more real folding or faulting, but a heck of a lot of sedimentation in these downwarping basins. This is a really good figure, even though it's drawn in sort of an, I like it, it's kind of a classic figure from an older computer generated diagram. Anyway, this shows the Sevier orogenic belt, which is again that Cretaceous time frame, and it kind of shows where these materials are today. So you can see that the subduction complex material, that's the Franciscan group rocks in California. Right up here next to the arc in this downwarping forearc basin, these are the Great Valley sediments in California today. The arc itself is the Sierra Nevada mountain range, and of course the volcanoes are long gone, but we actually see down deep into the pile with all these intruding granites and granite-like rocks. Then if we move further east, we get into the fold and thrust belt, right? The area that was intensely folded and faulted during these orogenies, and that's mostly as we fan out across Nevada, the Sevier thrust belt. And then when we finally get into Utah, we see there's those thick sediments that were being deposited in these downwarping basins, right? This is Paleozoic rocks underneath, and then the younger Mesozoic rocks on top. And of course, look where the Precambrian ends, right? Here in Nevada. Remember, during the Precambrian, right, part of this crust went away. So all of the western part of Nevada and California in this region doesn't have any Precambrian, right? It's been built out of accreted terrains and then intruded with granites. So this is neat. It gives us kind of a nice look. And on our field trip, we'll be driving from this part of the world, right? If you go even further, you'd see the Grand Canyon kind of rocks. And then as we go further west, we get into these more and more, marine rocks, and then into the folds, and then into the granites. And then if we kept going, we'd get into these subduction complex rocks. Here's a simpler diagram showing about the same thing. So subduction complex, coast ranges of California. Batholiths, of course, eroded down to Sierra Nevada mountain range. Thrust belts, Nevada, and these almost undisturbed but thick sections of sediment over in Utah. So that was the Sevier orogeny. The Sevier orogeny was the subduction and the fold and thrust belt. There was a later orogeny called the Laramide orogeny, and the Laramide orogeny sort of takes over after the end of the Sevier. And what's believed to have happened is the plate, instead of subducting downward all the way deep where you get melting and all that, that they think that the plate flattened out for some reason. And that flattening out of the subducting plate kind of popped up. What they're trying to show here is that this part of the world has been sort of uplifted. So this flat subduction allowed this part of the world to sort of be popped up. So domes, basins, monoclines, anticlines, and high angle reverse faults, right, that these things formed during the Laramide orogeny. Many of the larger faults that we see around the West that are involved in the Laramide orogeny, we think are those reactivated Precambrian faults. So to put this in a nutshell, you have the Sevier orogeny going on in the middle to later part of the Mesozoic, which is giving us the classic arc, back arc, thrust belt and everything. And then later on around the West, we're going to see the imprint of this Laramide orogeny, which is really just the sort of popping up of regions, which is why the Grand Canyon is so high. And we see lots and lots of around the Colorado Plateau. We think the reason the Colorado Plateau is popped up to this high level is part of this Laramide orogeny. And that's it for the Mesozoic. So, we leave the Mesozoic having deformed our Paleozoic and Mesozoic sediments in this island arc orogeny of the Sevier orogeny, right, along that west coast of Pangaea. Pangaea is broken up now into its various parts, Gondwanaland and Laurasia. So we end up heading into the Cenozoic with a very different place than what we started with in the Mesozoic. Of course, here's what the dinosaurs could have died by, but next week, right, we're going to go ahead and talk about Cenozoic tectonics, which I've told you before is that Farallon plate, which has been subducting underneath North America during the Mesozoic, is finally going to run into some trouble, right? It runs into North America, and it actually, the spreading center here gets subducted under the North America itself, and that's what we think is going to start the Cenozoic extension. So I'll see you next week. Take your quiz. Good luck, and I'll talk to you later.